Example 7. X minus 3 squared is less than or equal to 0. You might think at first that you should square this before you try to solve it. But this is different than example 6. So let's take a minute and compare the two. So if we go back up to example 6, the reason it's different is really because of this right here and this right here. So we had some things outside of the square that we had to combine with this before we could solve it and get that inequality with 0 on one side. But if you notice in example 7, 0 is already on one side and there's nothing over here except for the square. So for that reason, we don't want to square this because it's already factored, and squaring example 7 would be moving in the wrong direction. So we can start by just looking for the boundary numbers. And remember, the boundary numbers are where the inequality is equal to 0. So we're going to take this inequality and solve the related equation. Now there's a couple ways you can think about this. One is, remember that x minus 3 squared is equal to x minus 3 times x minus 3. So you can see it's already factored. And remember that zero product property. If you have two things that are multiplied together and get you 0, one of those, at least one of them, has to be 0. So we can take each one of those factors, set it equal to 0, and what we see is we get the same answer for each one. So what that means is that this is a double root. When we get to Unit 3, we'll talk about why the graph behaves the way it does at a double root. But that means there's only one x-intercept. And that is at 3, 0. So if we graph our quadratic function, or the parabola, we only have one x-intercept, and that's at 3. Now we need to figure out, is this going to open up or down? So remember that a is, when it's written like this, is usually factored out here. And so the coefficient is positive, so it's going to open up. And since it only has one x-intercept and it opens up, it has to touch at 3 and then turn. So this x-intercept is actually the vertex of the parabola. So when it has a single x-intercept, that is the vertex. So it actually kind of lies on the x-axis. Now, if we think about this, we want to know where this is less than or equal to 0. So we know that it was equal to 0 when x is 3, so that's one solution. But if it's less than, we want to know where it's also below the x-axis. Well, it's never below the x-axis. So this is another special case. The solution is a single number, not an interval. And when you're writing a solution that's a single number in interval notation, you use these curly braces, and the solution is just 3. Now, Alex has some other problems that are related to this. So let's talk about some what ifs. What if the equation had been x minus 3 squared, and instead of less than or equal to 0, it was just less than 0? The graph is not going to change. We don't want where it's equal to. We only want to know where it's below, and it's never below. So this would be no solution. Let's look at another what if. What if it had been x minus 3 squared is greater than or equal to 0? Well, in this case, it's greater than 0 on either side of 3. It's equal to 0 at 3. And so this is going to be all real numbers. Let's do one more what if. What if it had actually been x minus 3 squared is just greater than 0, and we took off the equals? What number would we have to exclude from the set of real numbers if we don't care where it's equal to 0, only where it's greater than? Well, we would have to leave 3 out of that solution, wouldn't we? Because 3 is what made it equal to 0. So in this case, we would say from negative infinity up to 3, union 3 to infinity. So that's another special case. And again, it really depends on what our inequality is as to what we write for the solution. So a lot of things to pay attention to. And when you're ready with all your work, you need to go back to the inequality to decide, what is my solution? What am I actually looking for?